Hello viewers on YouTube. In this video tutorial, we are going to consider electric currents. We are going to go over some of the terms associated with electric current, and we are going to go over some examples. Now, some of these terms include Ohm's law, electric work done, electric power, E.M.F, potential difference, and resistivity. So first and first, let's begin with the definition of electric current. Electric current is simply the rate of flow of electric charge along a conductor. Symbolically, electric current is represented with capital letter I, and mathematically it's equal to the quantity of charge divided by the time taken for that charge to move around the circuit. Electric current is measured in ampere, and since the charge is in coulombs and the time has to be in seconds, so 1 ampere corresponds to 1 coulombs per second. Now there's something called E.M.F. E.M.F means electromotive force. Its function is to help maintain a consistent flow of charge along the conductor, and is being developed by a cell or a battery. Now in terms of definition, E.M.F is the total work done in moving 1 coulomb of electricity around the circuit. And interpreting this, mathematically E.M.F is equal to the work done divided by the quantity of charge. So you must have the total work done in deriving this quantity of charge with its magnitude in order to find the E.M.F of that cell or battery. Now we also have another quantity that works like E.M.F, though there's a difference between that quantity and E.M.F. This quantity is called potential difference, written for short as PED. And one good thing about it is that it's measured in the same unit as E.M.F. They are both measured in volts, V-O-L-T. Now, what exactly is potential difference? And what makes it different from E.M.F? Potential difference is the work done in driving a unit positive charge from one point to another. However, to determine its magnitude, there's a law that is supposed to do that. And this law is called Ohm's law. And interpreting the law, potential difference PD turns out to be equals to IR. So sometimes, instead of PD, you might have it as V equals IR according to Ohm's law. But keep in mind, it's also measured in voltage. So now what makes it different from E.M.F? What makes it different is that potential difference tells us the energy difference between 2 point charges, either from a high potential region to a low potential region, while E.M.F works is to move charges from low potential to high potential and continue the process. So that's what makes it different, but they are measuring the same thing. It is when the charges are moving here and there, you can determine the potential difference, except if they are moving from a high potential to a low potential, because it's obvious that charges move from a high to a low by themselves. So that's the difference between E.M.F and potential difference. Perfect. Now that you know what electric current is, likewise potential difference. Now what about this R? It means resistance. And what resistance does is that it opposes the flow of current. Resistance and electric current are inversely related, which simply means that when a conductor has a high resistance, then the current flowing through the conductor will be very less. And when the current passing through a conductor is very high, then this tells us that the resistance in that conductor is very, very less. So that's the relationship between current and resistance. Now, experiment shows that the resistance of a metallic conductor is related with the formula. And this formula tells us that R is equal to rho multiplied by L divided by A. It tells us the relationship between the length of that conductor and the area of the conductor. This simply means that the resistance of any metallic conductor depends on the magnitude of its length and its area. Likewise, the value of rho. Rho tells us the resistivity of the resistance. The higher the value of rho, the higher the resistance of that conductor. And this works in the vice versa way. Now sometimes you might be required to find the value of rho. Rho means resistivity, okay, and rho Isolating a row, we have it to be equals to the resistance multiplied by the area divided by the length. Now what about the units? Resistance is measured in ohms, area is in meter squared, and length is in meter. So meter squared can reduce to meter, and we have resistivity to be in ohms, meter. E.M.F, like I said, and potential difference are in voltage, while electric currents are in ampere. Now what about electric work done? Electric work done, you have to be very sensitive while dealing with it, as 3 formulas help us to find the electric work done. However, these formulas, you have to be careful while identifying the one to use. First, let's begin with the definition of electric work done. Work is said to be done when an electric current moves from one point to another in an electric circuit. Now, sometimes we might need to find the total work done developed by an entire system or within an entire electric circuit, while sometimes we might just need the work done in driving a unit's positive charge or the energy developed within a resistor. Now, in either case, the steps you have to take are different. So that's why I said you have to be very careful. So, interpreting the definition of work done using E.M.F, isolating W, we have W to be equals to the E.M.F, which I will write as E.M.F in my start, multiplied by the quantity of charge. Now, since E.M.F is measured in voltage, we can write this as W equals to V times Q, which is the same thing as VQ. However, you need to understand that that V must be the magnitude of the E.M.F of that cell or battery. And this W will tell you the total work done, okay, developed by the entire system or within the entire electric circuit. Because until the E.M.F runs out before work will stop. Otherwise, work will continue to be done. Are we together? So it will tell you the entire work done by the system. Perfect. Now, from the definition of electric currents, we said I is Q over T. What if we solve for Q? This is that Q will be equals to IT. Now, since this refers to the quantity of charge, then we can replace IT with Q. So therefore, the work done, total work done to C is simply equals to V times IT. And this is the same as IVT. So, in case you are given the electric current, the potential, the E.M.F, and the time for that charge to move around the circuit, then you can always have the total work done in moving the charge around the circuit. And if there's a voltage that is given and the quantity of charge, that can also help you to find the total work done. Now, what if you want to find just the work done in moving a unit's positive charge? Not necessarily all the charges within the system, but the unit's positive charge. Now, how can we do that in this case? To find the work done in this case, we will need to consider Ohm's law. Now, the potential difference we'll be considering in this case will be, the voltage we'll be considering in this case will be the potential difference. Now, since we said that W is equals to VQ, now the V in this case won't be the E.M.F. The E.M.F is for all the charges within the system, but the potential difference is for a unit charge. So therefore, W in this case will be equals to VQ. I've written that already. Now, from Ohm's law, we said V is equal to IR. So instead of V, we can put IR. Then we have W equals to IR times Q. However, from here as well, we said Q is IT. So therefore, we can have W to be equals to IR multiplied by T. And this, IT multiplied by IT. And finally, the work done in moving a unit positive charge around the circuit can be calculated with the formula I squared RT. So that's it. Please be careful. If you are required to find the total work done developed by a system or in moving charges from one point to another, then in this case you are using these two formulas or any of them. While if you want to find the work done in moving a unit positive charge, then in this case you have to use this other one. Are we together? Perfect. So these are the formulas you have to be familiar with while dealing with problems involving electric currents. But I almost forgot. What about electric power? To find the electric power in moving a unit positive charge, we notice that for magnets, power is simply the work done. P, that means a red color. P is work done divided by the time. Now we say that work done is IVT. So now if there's IVT, that's the total power developed. P will be equals to IVT divided by T. Now the T cancels and we have IV. So once you have the current and the voltage, which will be the EMF in that case, because we're considering total power developed, then P will be IV. Now if it is the power developed by just a unit positive charge, then in this case we are using I square active. So if we plug in I square active for W, we have I squared RT over T, which is the same thing as I squared R. So P is I squared R. So please know when to use each and every of these formulas. And I hope you find this understandable and helpful. Now let's try to go over some examples to ease our understanding. On to example number 1. The headlamp of a car takes a current of 0.4 ampere from a 12 volt supply. The energy produced in 5 minutes is dash. Now whenever you are asked to find the energy, you can always think of the work done, because they are both measured in joules. I know the work done in moving the positive charge tells us the energy in moving it exactly. So therefore, we are constantly using the formula for the work done. Now, which of the formula are we using? What would you say? Now, since the question asks us to find the energy produced in 5 minutes, and the voltage given to us is the EMF, as considered a 12 volt supply. That means that cell or battery, whatever it is that is being supplied to that headlamp, has a 12 volts. So that's the EMF. I would say that this is not the potential difference between 2 points. That tells us the EMF. So therefore, we are using one of the first two formulas for the total work done developed by a system. But first and foremost, let's write out what we know. The current is given as 0.4 ampere. That makes sense, as it is in its appropriate SI units. Now secondly, the EMF, the voltage, is given as 12 volts. And finally, the time is given in 5 minutes. However, it has to be in seconds. Minute to seconds, you multiply by 60. That gives us 300 seconds. Now at this point, what formula should we use? Should we use W equals QV, or we should use W equals IVT? What would you say? Well, we can investigate that using what we are given. Notice that using this will be the best one, as all the quantities are given. So we are good to use the second one. Now you might be wondering, why did I use W? Since this energy, please you can use E. So E is still equal to IVT in this case. Okay, the energy and the work done gives us the same results. So therefore, the current, which is 0.4, multiplied by the voltage, which is 12, then multiplied by the time, which is 300. Now multiplying this using my calculator, 0.4 times 12 times 300. So I got 1440 joules. So this is the energy produced in 5 minutes. And that's the solution to example number 1. On to example number 2. Feel free to pause the video and figure this out yourself. After that, you can unpause it to see if you got it right. An electric lamp is marked 240 volts, 60 watts. What is the resistance when it is operated at the correct voltage? So just like before, let's write out what we know. The goal is to find the value of R. So what would it be? We are given the voltage. V is 240 volts. Now we are given the power. Well, I think when I was discussing about power earlier, I forgot to make mention of the units. The power is measured in watts. So whenever you're given any magnitude in watts, knows that it is the power. So 60 watts. Perfect. The goal is to find R. So what formula of the power involves R? If you recall, earlier we said the power developed in moving a unit positive charge is simply given by the formula P equals I squared R. So this formula definitely works out. Now, since this is the best one to use, from there you can clearly say that the voltage given is the potential difference and not the E.M.F. So as the power is 60 and the current, well, the current is not given, so definitely we can make some arrangements from Ohm's law. Now, since V is equal to IR, then I will be equal to V over R. So then we replace V over R with I right here. So definitely P will be equal to V over R all squared to multiply by R. Then expanding the bracket, we have V squared over R squared multiplied by R. Now R reduces, we have P equals V squared over R. Now since the goal is to find R, we have R to be equal to V squared over P. Now therefore, since the voltage is 240, we have 240 R squared over P, and P is 60. So if I stabilize my calculator, 240 times 240, I got 57,600. So therefore, on our way to the final stage, the resistance becomes 57,600 divided by 60. And if I divide that by 60, I got 960. So the resistance is simply 960 ohms. Like we said, the resistance is measured in ohms. And that's the solution to example number 2 as well. On to example number 3. What is the resistivity of a cylindrical material wire whose 1.0 meter length has a resistance of 2.0 ohms? The diameter of the wire is 0.5 millimeter. The goal is to find the resistivity. Earlier, we said that the resistivity rho is equal or is given by the formula Ra over L. So now, let's figure out what we know. We are given the resistance of the wire, and that's 2.0 ohms. We are not given the area, but we can definitely find the area. Now, we are given the length of the wire L, that's simply 1.0 meter. Now, instead of the area, we are given the diameter D of that wire, that's 0.5 millimeter. However, since diameter is a distance, it has to be measured in meter. Millimeter to meter we divide by 1000. So 0.5 divided by 1000 gives us 0.0005. So we have 0.005 meter. Now, notice that the main measure of cylindrical material, but we are not given the height of the cylinder. So definitely to find the area, we are considering using pi r squared, which is the area of the circle, just a flat surface. Well, assuming you are given the height, then you're using the area and the formula for the volume surface, like the conic part. Perfect. So therefore, area, which is pi r squared, will be 22 over 7 multiplied by the radius. If we divide this by 2, that will give us 0.000025. So multiply by 0.000025 all squared. So if I just square that, then multiply by 0.00025, and again multiply by 22 over 7 in the bracket, 22 over 7. Okay, I end up having this. That's 1.96 times 10 raised to the power of -7. Now that we have the area, we can proceed on finding the resistivity. So finally, resistivity will become the resistance, which is 2, multiplied by the area, which is 1.96 times 10 to the power of -7, and divided by the length, which is 1. So finally, if we multiply this by 2, that should give us 3.86. So we have 3.86 times 10 to the power of -7. Since the resistivity is measured in ohms meter. So that's our final answer to example number 3 as well. And that's how to easily find the resistivity of a metallic conductor. I hope you find this helpful and understandable. Thank you. See you in the next video. By the way, you can subscribe if you want to. Thank you once again. Bye for now.